everyone. We're getting very close to the goal. We still got some more hard work to do, though, so let's get started. And our next result is another sort of technical kind of result. And the statement is a bit of a mouthful, so here we go. So let's let K equal, I'm going to call this L0, contained in L1, contained in ... contained in, and we're going to go up to L sub m. That's going to be L. With L sub I equal to L sub I minus 1 adjoin, I'm going to call that, oh yeah, that's beta sub I, where beta sub I lives in L sub I. Where beta sub I raised to the exponent I'm going to use is an n sub I, is an element of L sub I. In other words, what I'm saying is that L over K is a radical extension, but I'm setting up all the notation for this. So we can say that is. This isn't really part of the statement of the theorem, but just to keep your head straight. So that is L over K is radical. So you can include that or not include that as you see fit. So if the characteristic of K does not divide the product of these exponents, so does not divide n1, n2, oh, am I doing n0? No, I don't need an n0. So yeah, n1, n2 up through n sub m. Then there exists an extension so this exists an extension and of L, so let's call this M, so this will be M over L, such that M over K, M over K is radical and Galois. Okay, and this is going to be a key theorem. We'll need this in the next big theorem that we're going to prove. So it's sort of the last main step along the way here, and the proof is by induction on M, right? So on the length of the radical extension. So this is induction on little m. So first of all, if m equals 0, then k equals L, which equals m, and we're done. So if m equals 0, then k equals L equals m, and we're Galois and sort of radical by default, so we're good. So now, let's assume the result holds for length m minus 1. So for length m minus 1. So what does that mean then? So then there exists an extension, I'm going to call it m prime. Yeah, m prime. So then m prime over L sub m minus 1. That is radical and Galois. Right, so this is our inductive hypothesis. Now, so now we have beta sub m that lives in that should be an m, right? That lives in L sub m, which is L sub m minus 1, adjoin beta sub m, and when you raise beta sub m to the, what was my exponent? I think it was n sub m. Let me make sure that's right. Yeah, n sub m, that lives in L sub m minus 1. Now, I don't want to use a whole lot of subscript, so let's just say, so let's let mu, this is going to be the minimal polynomial. So this is a mu. It's probably maybe a bad choice, but so okay. I did it in my notes, so I'm just going to use it. That's a mu right there. This is going to be, so this will be an L sub m minus 1 bracket x. So this is the minimal polynomial. For beta to the m over L sub m minus 1. Okay, but now, okay, so this polynomial has coefficients in L sub m minus 1. L sub m minus 1 is contained in m prime. So we can view this polynomial as living in m, or having coefficients in m prime as well. So viewing mu in m prime bracket x, call it lambda now. So let's let lambda in m prime bracket x, yeah, m prime bracket x be an irreducible factor of mu, right? So I mean, mu is just the polynomial. It lives in L sub m minus 1. If we view it here, right, it may or may not be irreducible over m prime. If not, factor it as far as you can and choose an irreducible factor. And the reason I'm trying to set up Kroneker's theorem now, so by Kroneker's theorem, what? Well, if we got this irreducible polynomial, there exists an extension that contains a root of lambda. And, okay, so I'm going to call it m prime sub gamma. Okay, so by Kroneker's theorem, there is an extension. And remember, you can obtain that extension by adjoining a single root. So there's an extension. So I'm going to call it m prime adjoin gamma of m prime that contains a root gamma of lambda. Oh man. You know, sometimes, oh, this is terrible. The entire box of chalk is crumbled little bits. That's the biggest piece. And you know, you've never heard me whine about chalk. The chalk here at Cal Poly breaks constantly, and most of the pieces are this size in this box. I can't write with this. It kills my hand. So I'm gonna have to pull out. This is usually my backup chalk. I use this on rainy days, and a student got this for me a long time ago, and so I've used it very, very sparingly, but Hagoromo, that's the best chalk ever. And you can't get the real Hagoromo anymore. Okay, where am I? So now, what do we have? We have an extension of m prime that contains a root of lambda. Now, let's let I from L sub m minus 1 into m prime adjoin gamma be the inclusion, right? So what do we have? L sub m minus 1 lives inside capital M prime, which lives inside, or it could be viewed as living inside M prime adjoin gamma. So we can think of this inclusion mapping right here. Now, since I of what is that? Oh, sorry, I couldn't read my own writing there. I of m. That should be a mu. I of mu of gamma equals 0 by, remember our famous theorem 2.5, there exists an extension which I'm going to call J from L sub m minus 1 adjoin beta sub m to m prime adjoin gamma, right, that takes one root to another, right? So it's going to take beta sub m to gamma. So such that J of beta sub m equals gamma. Okay, so now, thus, we can view both L sub m, which is L, right like this. So L, which equals L sub m minus 1 adjoin beta sub m, which is isomorphic to the image of J. So and M prime as subfields of M prime adjoin gamma. Okay, so now the Hagoromo's not it's supposed to erase good, but it's actually leaving a bit more marked than I thought. Okay, so now apply our previous theorem. So this is theorem 6.5. So here's how it works. By our inductive hypothesis, so M prime over K is Galois. All right, that was our inductive hypothesis. And so, and beta sub m is a root of x to the n sub n sub m minus beta sub m raised to the n sub m, where beta sub m raised to the n minus m lives in, where does that live in? M prime, right? Yeah, M prime. M prime. So there exists a radical extension M over M prime adjoin beta sub m such that m over k is Galois. So that was the content of, or that's the application of theorem 6.5, right? We get this extension right here. Now, so now we've got the Galois part. We just need to show that it's radical. So it remains to show that m over k is radical, but this follows just by doing it piece by piece. So this follows from the fact that the following extensions are radical. M over M prime adjoin beta, right? That's what we got from induction. M prime adjoin beta over, is it beta? Sorry, that should be beta sub m. Beta sub m right there and right there. Over m prime, right? Because we're extending beta sub, or adjoining beta sub m, right? Which is our radical element. And the last one, m prime over k, are radical, right? So the last steps of the, so what do we have? This part is obviously radical. This we got by our inductive hypothesis. This was by assumption. Well, not quite by assumption, but by, that was by our inductive hypothesis. And so putting those three pieces together, right, tells us that m over k is radical as well. Okay, we're ready to prove what I guess you could consider the main theorem of the class now. And it's essentially just putting a bunch of stuff together that we've already proved, but it's going to take some more. So this is theorem 6.7. So we need a radical extension, so I'm going to set this up. So let's let, it's going to be the same notation as we had in the last theorem. So let's let k equal L0, contained in L1, contained in L sub m, which equals L, where L sub I equals L sub I minus 1 adjoin somebody, let's say beta, what did I use here? Beta I, right? Beta I. And beta I raised to some power m, and what did I use here? Oh, no, n sub I is an element of L sub I minus 1. Right, so what do we have now? We've got a radical extension L over K. Oh, and we'll say and assume that the characteristic of K does not divide the product of these powers, so n1 up through n sub m. n1 up through n sub m. So now, if we have a polynomial, f in k bracket x splits over L, then the Galois group, gamma of F is solvable. One quick note before we start the proof. So let's say note, when the characteristic of K equals 0, then this assumption right here we don't need to worry about. So when characteristic of K equals 0, we can state the theorem as if F in K bracket X is solvable by radicals, then the Galois group of the polynomial is solvable. Right, because that's what this says, right? If you've got a radical extension and your polynomial splits over L, that is by definition what it means to be solvable by radicals, right? We just, in the most general setting, we have to throw in this bit about characteristic not dividing the product of the polynomials. So I'm going to do this proof in 4 steps, and I don't think I'm going to actually finish. I'm going to probably just do 2 steps now, and then I'm going to finish the other 2 in the next lecture, because I'm a little short on time today. So, okay, so here we go. Step 1. So by our previous theorem, so this is theorem 6.6, there exists an extension M over L, such that M over K is Galois and radical. So we might as well assume that L over K is radical and Galois, or we already know it's radical. Assume that it's Galois from the start. Otherwise, replace L with M and work with M. So Galois and radical. So thus, we can assume that L over K is Galois. Right. Otherwise, just replace L with M and then go from there. Okay, so that's step 1. And that was the whole point of the previous 2 theorems, essentially, is to be able to say this right here. That when we have an extension that's radical, we can actually assume that it's both Galois and radical. Otherwise, extend it right to this M. Okay, so step 2. Okay, so now let's choose an I between 1 and M. So let's let I be some number between 1 and M. Now, since L over K is Galois, hence normal, and we have K contained in L sub I contained in L. By theorem, corollary 3.4, L over L sub I is normal, by 3.4, corollary 3.4. And separable that is, what's that, 4.1, I want to say. Yeah, theorem 4.1. Okay, and of course, since L over K is finite, so is L over L sub I, right? So since the degree of L over K is finite, so is the degree of L over Li. Thus, L over Li is Galois. If you noticed, I stopped the video, and after I finished that last theorem, I stopped the video. I went downstairs, grabbed 2 new boxes of chalk. Both of them, everything was shattered. I got 4 pieces of chalk. This is the piece of Haggeroma I was using. It's getting a little too short for my hand, so I'm gonna have to switch over. 4 pieces of chalk out of, I don't know how many is in normally box. How much is in the box? Oh, I think 20. No, not 20. 12. Okay, so out of 24 pieces, I got 4 pieces of chalk that weren't broken. All right, so we know that L over L sub I is Galois. So now, let's write theta sub I. That's going to be beta I raised to the, n sub I, which we know lives in L sub I minus 1. Then I want to consider this polynomial, so viewing the polynomial x raised to the n sub I minus theta sub I, so this is going to live, well, it lives in, this coefficient lives in L sub I minus 1, which is contained in L sub I, so this, I want to view that in L sub I bracket x. We have that beta sub I is a root of this polynomial, right? So of that's a root of this polynomial. But L over L sub I is normal. And so what do we know then? It has to split over L. Right? So since L over L sub I is normal, the polynomial splits over, so let's write it out, x n sub I minus theta sub I splits over L. Now, we know exactly what the roots of these look like, and so all right, so we can say thus. So let's see, what will these look like? They'll look like, well, so beta sub I, comma, epsilon beta sub I, comma, epsilon squared beta sub I, dot, 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 epsilon to the n minus 1 beta sub I, lives inside L, where epsilon is a primitive oh, is this an n sub I? Probably, huh? Yeah, n sub I, that should say n sub I minus 1 right there, is a primitive n sub ith root of unity, right? So this is the entire collection of roots. Since this polynomial splits, all the roots have to live in L. Now, of course, since beta sub I lives in L, and all of this stuff lives in L, that tells us that epsilon lives in L as well. So since beta sub I is an element of L, we have that epsilon is an element of capital L. All right, so now I'm going to call this G. So let's write G equal to, oh no, G sub I is going to equal the cyclic subgroup generated by epsilon sub I. This we'll view as a subgroup of L, I guess we're going to write L star, right? Yeah, L star, the multiplicative group. Now, so then, the group G, which is going to be the direct sum of all these G sub I, so G sub 1, sum G sub 2, dot, 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 sum G sub I, no, I think I want G sub what? G sub M contains the cyclic group, and this will be generated by the product of all these epsilon sub I. So epsilon 1, epsilon 2, dot, 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 epsilon, epsilon M, which has order. Okay, so now what's the order of that going to be? It's going to be the least common multiple of the orders of the individual ones, so which has order. Let's call it little n equal to the least common multiple of the orders of the individual ones, which are the n sub i's. So n1 up through n sub m. Thus, L star, got a sneeze stuck now. Thus, L contains L or L. I mean, I don't really need L star, do I? Thus, L contains a primitive nth root of unity. And let's call that epsilon. Right? I mean, who is that? Who is this epsilon? It's any generator of this cyclic group right there. That group has order n, right? And so it's an nth root of unity. Okay, so now I'm going to define L prime equal to, so this is going to be, no, L sub I prime equal to L sub I adjoin, oh, my eyes aren't working, that's an epsilon though. L sub I adjoin epsilon. Now, this gives us the following setup. So it's going to be K contained in L0 prime, or is that equal? No, contained, equal, or contained in L1 prime, contained in dot, 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 contained in L sub M prime. And by the way, so L sub M prime, right, that's going to be L sub M adjoin epsilon. L sub M is L. Epsilon lives in L, so when you adjoin, nothing new happens here, so that one is L. Okay. That that's the end of step 2, and this is where, yeah, I'm gonna just have to stop now. Sorry, and I'm gonna finish the step. So we've set the stage, right, to move on and actually analyze the Galois group, right? So we want to show that the Galois group is solvable, and we're sort of setting the stage to get to that situation. So we'll see you next time.